Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael C. Ndinechi. Our topic today is Module 033, Single-Phase Alternating Current Circuits. Please follow me in the Engineering Lecture Series by subscribing to my YouTube channel at https://youtube.com/@Nigeria@Ndinechi Michael C. Like, share, and drop your comments in the comment section or reach out to me using my email addresses. You can listen to my earlier lecture on circuit theorems in Module 025, Part 2, using the link given, and Part 1, Module 025, using the link given. I also expect you to listen to my lecture on electromagnetism and electric circuits on Module 021. Also, we've talked about applied electricity on Module 020 using the link. Today, we are looking at alternating current circuits. The first thing we look at is the alternating current in a purely resistive circuit. In our earlier lecture, we've looked at different circuit elements, but three are outstanding, and that is the resistance, the capacitance, and the inductance. Now, if your circuit is containing only a resistor, you say that that circuit is a purely resistive circuit. So today, we are going to consider three of them: the purely resistive circuit, the purely inductive circuit, and the purely capacitive circuit. Then we will look at when a circuit contains three of them or any combination of two of them. And finally, to take us to what happens when certain conditions are met, which will give rise to resonance, and the application of such in engineering and telecommunications. So let's look at the alternating current in a purely resistive circuit. Okay, if we consider a circuit possessing only a resistance R ohms, which we term purely resistive circuit, connected across the terminals of an alternator A, as shown in Fig. 1. Now, supposing the applied alternating voltage is a sine wave, as shown in Fig. 2, then the value of the voltage at any instant in time, t, is V volts, and the value of the current at that instant in time is given as I equals V over R amperes. That equation represents the Ohm's law we've been talking about in our past lectures. Now, when the voltage is zero, automatically the current is also zero. So you look at the diagram we talked about, Fig. 1, we have said when you see a small circle with a coil line inside, it means that it is an alternating supply and not a DC. So you see our alternator there representing the alternating supply, then the R, which is the resistor. So we are saying that when this alternator is supplying a pure sine wave, then the current, if you look at the current, the dotted line in fig 2, then the voltage, which is the solid line, will be in phase. And we say, when we say that the voltage and the current is in phase, it means that they are crossing the zero line at the same time. Even though the peak value of V is higher than the peak value of I. But you see that two of them are crossing the zero line at the same time. So we say that the voltage and the current are in phase. But if you look at that, you see that the amplitude of V is bigger or higher than the amplitude of I. And I would like you to try to prefer the reason why the amplitude of V is higher than the amplitude of I. So, since the current is proportional to the voltage, then the waveform of the current is exactly the same as the waveform of the voltage. Also, the two variables are in phase with each other. That is, they pass through their zero values at the same time or at the same instant and attain their maximum values in a given direction at the same instant. Hence, the current value will be as shown in fig 2 using dotted lines. If Vm and Vi were the maximum values of the voltage and current respectively, then from Ohm's law, I max will be equal to V max over R. We note that as equation 1. But we know that the root mean square, that is the R.M.S value of a sine wave, is 0.707 times the maximum value, so that the R.M.S value of current will be equal to 0.707 Im, while the R.M.S value of voltage will also be equal to 0.707 Vm. So if we substitute these values in equation 1, it will now give us I over 0.707, which is equal to V over 0.707R. So it cancels out to give you I equals V over R, which is the Ohm's law. So you see that nothing changed, but when you are looking at current and voltage, it's not always that you just use V and I. At times, you may be required to use the R.M.S value, more especially when it is an alternating value. That is, it's a sine wave or a cosine wave. There is no difference between a sine wave and a cosine wave except that at origin, the sine wave will be 0, and at origin, a cosine wave will take maximum value 1. So again, this R.M.S value of any signal shows the 3 dB point, where if you recover the signal from that point, no information will be lost about the signal. And it's called the R.M.S value, that is root mean square value, and it is always given as 0.707 times the maximum value of the quantity you are looking out for. So we said self-test 1. Do we really have a purely resistive circuit in real life? In that our fig 2, where is the amplitude of Vm higher than that of Im, since we say that both the voltage and the current are in phase? Please submit your answer in the comment section. I will go through and try to provide you with the correct answer. So now, hence, Ohm's law can be applied without any modification to an AC circuit possessing resistance only. Very important. Ohm's law can be applied without any modification to an AC circuit possessing resistance only. Now, if the instantaneous value of the applied voltage is represented by V equals Vm sine theta, then the instantaneous value of current in a resistive circuit will be I equals Vm over R sine theta. That is, that V showing small v equals V showing instantaneous value and the peak value sine theta. So when we do that, we have equation 3. Now, say that the phasors representing the voltage and current in a resistive circuit are actually coincident, as shown in fig 3, but are drawn slightly apart so that the identity of each may be clearly recognized. So if you look at that fig 3, you see 2 lines. The longer one is the V, and the shorter one is the I. We are saying that the two is supposed to be the same line, because we say that they are in phase. But just to be able to identify the magnitude of the current and the magnitude of the voltage, they are drawn very small space apart, as you can see in fig 3. So the voltage is always higher than the current because the resistance is what makes the value of the current not to be equal to the value of the voltage. So we can also look at the current and voltage in a purely inductive circuit. Now, say if we consider a purely inductive circuit, as shown in fig 4, if the instantaneous value of current through the coil of inductance L Henry and a negligible resistance can be represented as small I. Remember, we use the small letter I to represent the instantaneous value, so that it will be given as Im, that is the peak value of I, times sine theta. If you look at this equation 4, you will be seeing small letter I. We say that small letter I represents the instantaneous value, while the capital letter I represents the maximum value. So at any point in time, this value of current is changing, and is changing following the pattern of sine theta. That is the angle of inclination. So we say the instantaneous value, small letter I, is equal to the maximum value, Im, times sine theta. So if you do that, it gives you also Im, maximum value, Im sine 2 pi ft. If you change theta to its radians, it becomes 2 pi f. So say that gives us equation 4. So where t is the time after the current has passed through 0 from negative to positive values, which we show in fig 5. And from our earlier lecture, that is the models I talked about on slide 2, model 021 and 022, we have said that the induced EMF, when we say EMF, electromotive force, in a coil will be a function of the rate of change of current with time, and will be equal to EMF equals E equals minus L di dt. This is very important for noting that the EMF induced in a coil is a function of rate of change of current with time, and is equal to minus L di dt. Now, from what we have said in the above equation, we have said that I is equal to Im sine 2 pi ft. So if we substitute it in the above equation, where we say that E is equal to minus L di dt, then you will have that, and when you differentiate that with respect to t, you have that it is equal to minus 2 pi f L Im cos 2 pi ft, when you differentiate that. So it now gives you, because we are looking at sine, we want to convert that back to sine, then it will be 2 pi f L Im sine, in bracket, 2 pi ft minus pi over 2. From your trig identity, this will not be an issue for you. You did your differentiation, you got your sine to come as a cosine, and you do your shift, because the difference between cos and sine is that one starts at the peak, the other one starts at 0. So if you move the 10 by pi over 2, they become the same. So we got the 10 back to our sine because we are using sine. So we call that equation 5. Now, when t is equal to 0, cos 2 pi ft will be equal to 1. Induced EMF will be minus 2 pi FLIM when t is equal to 0. Very important to note this. When t is equal to half f, that is the frequency of the wave, then cos 2 pi ft will be equal to cos pi, which will be equal to -1. And induced EMF will be 2 pi FLIM. Now, since the resistance is negligible, the applied voltage is absorbed in neutralizing the induced EMF. Therefore, the instantaneous value of the applied voltage will be instantaneous value, small v, equals 2 pi FLIM cos 2 pi ft, which will be equal to 2 pi FL I max sine in bracket 2 pi ft plus pi over 2, because we want to move it back after the integration. We want to move it back to sine. So we have equation 6. Now, if you look at the figure, which we call figure 4, you see that it is just representing a circuit with only an inductor. In real life, we don't have a pure inductive circuit or a pure resistive circuit, because even the wire you use to connect your resistor is generating some flux around it. So it is not very, available in real life, but we are just doing this to do an analysis to get something. But in real life, you expect to have this inductor having its own internal resistance. But for now, we are neglecting it, or we are assuming that it is negligible. So now, if we compare equations 4 and 6, we will see that the applied voltage leads the current by a quarter of a cycle. And from equation 6, the maximum value Vm of the applied voltage is 2 pi FLIM. That is, Vm is equal to 2 pi FLIM, when we say Im, the maximum value of I. So that Vm over Im will give us 2 pi FL. So if Im, Imax, and the Vm, which is the minimum value of V, be the R.M.S values, then V over I will be equal to 0.707 Vm over 0.707 Im, which is equal to 2 pi FL. That gives us the inductive reactance. So this reactance is like the resistance offered to the flow of current in the circuit when we have only pure inductive system. So we call this figure 2 pi FL the inductive reactance. This inductive reactance is expressed in ohms and is represented by the symbol capital X subscript L. Capital X subscript capital L. We call it the inductive reactance. So we now say that hence I will be equal to V over R, which is what we have known from our Ohm's law. In this case now, our R, that is the resistance in the circuit, is 2 pi FL. So our I will be equal to V over 2 pi FL, which is equal to V over XL, because we have said that the inductive reactance is represented by XL. We call that equation 7. And we note at this point that the inductive reactance is proportional to the frequency and the current produced by a given voltage. That this frequency and the current is inversely proportional to the frequency which we have seen in Fig 6. So now, if you look at Fig 5, we're looking at a plot where you have the instantaneous voltage as the voltage changes. You see the dotted curve, which is the induced EMF in the coil. You see the applied voltage, and you see the current. Important thing to note here is that the current is a sine wave, while the applied voltage is a cosine wave. You can figure out that because one starts from the origin, 0, the other one starts at the peak, 1. And the induced EMF is out of phase with the applied voltage by, if you look at it, by a quarter of the cycle. You can see where I.M is, where it crosses the line. So it tallies with what we said, that it leads by a quarter of the cycle. So if you look at Fig 6, you can see the two plots. We say that in purely inductive circuit, the current varies like that, while the inductive reactance is proportional, a straight line passing through the origin. And to the right is the phasor diagram, that the peak voltage is 2 pi FLI and is 90 degrees out of phase with I. So, whereas in the purely resistive circuit, the phasor, that of the current and the voltage, is facing the same direction, so there is no variation. Then we look at current and voltage in a purely capacitive circuit. To say, if we assume that the instantaneous value of current through a capacitor of capacitance C farads and a negligible resistance, as shown in Fig 7, if we do the analysis, we will see that from our earlier lecture, module 021, that we have stated there that the induced EMF in a capacitor is a function of the rate of change of current with time and is equal to C dV dt. Also, the instantaneous value of voltage applied to the capacitor will then be instantaneous value small v equals Vm sine theta, just like before. In this case now, Vm sine 2 pi ft, equation 8. We have seen similar equation when we were looking at the purely inductive circuit. So if the applied voltage increases by dV volts in dt seconds, then the instantaneous current will be I equals C dV dt. Now, if we put that and integrate, because previously we have said that V is the instantaneous voltage V, or small letter v, is Vm sine 2 pi ft, So if we integrate it or if we differentiate it with respect to t, you will see that just like we've done in the inductive, it will give us 2 pi f c Vm cos 2 pi ft. Like before, you shift it back to get it to sine, it gives you plus 2 plus pi over 2, equation 9. So if we compare equations 8 and 9, it shows us that the current leads the applied voltage by a quarter of a second. And the current and voltage can be represented by a phasor as shown in Fig 8. From equation 9, it follows that the maximum value of I passing through a capacitive circuit is 2 pi FCVM. So if we do V over I, it will give us 1 over 2 pi FC. And say, hence, if I and V be the R.M.S values as before, Vm over Im will be equal to 1 over 2 pi Fc. And we say this is the capacitive reactance of that circuit. We've said that when we say capacitive reactance, we are looking at the resistance to flow of current being presented by the presence of the capacitor. So that resistance as provided by the capacitor is what we call the capacitive reactance of that circuit. And that we represent as equation 10. Now, this capacitive reactance, which is expressed in ohms and represented by a symbol XC, capital letter X, subscript, capital letter C. Therefore, I will be equal to 2 pi FC V, which is the same thing as V over XC. This implies that the capacitive reactance is inversely proportional to the frequency and that the current produced by a given voltage is proportional to the frequency. The variation of reactance and current with frequency for a purely capacitive circuit and the corresponding phasor diagrams are as shown. If you look at Fig 8a, you can see that it is the opposite of what happens in the inductive circuit. In the inductive circuit, it was the inductive reactance that is proportional, passes through zero, through the origin, while the current, is the curve. Whereas in this capacitive circuit, the current is the one that is proportional, passing through the origin, zero, while the capacitive reactance is the other one. And the phasor, like before, is 90 degrees. But the y-axis is I, while the x-axis is V. So there's more difference in the phasor diagram. So let's see what it leads us to. Now, we look at when we have these three elements, the resistor, the inductor, and the capacitor in a circuit. It could be in a series form, it could be in a parallel form. But let's just take a typical example where they are in series. So we say an actual electric circuit usually has resistance, capacitance, and inductance, or different combinations of any two of the circuit elements either in series or in parallel. So if we consider a series combination as shown in Fig 9, analysis of the phasor diagrams of purely resistive, inductive, and capacitive circuits will show that the potential difference across the inductor is given as 2 pi FLI. We have said that in the phasor diagram we drew for purely inductive circuit. And this lead to the current being led by 90 degrees, and the potential difference across the capacitor is given as 1I over 2 pi FC, which is lagging the current by 90 degrees. Very important to note this, that the PD across the inductor is leading the current by 90 degrees, and the PD across the capacitor is lagging the current by 90 degrees. So if it is so, it means that we can find the equivalent voltage drop across the three circuit elements: the resistor, the inductor, and the capacitor, based on the fact that we say that this one is leading while this one is lagging. Just by common sense, we know what we mean by leading and lagging. So if we do that, we can see that V squared is equal to Ri squared plus the two reactants squared. That is the inductive reactance. Because they are 90 degrees out of phase, you see this minus that. So if we solve out that, we arrive at equation 12, which is the same thing as the Ohm's law, which says that I is equal to V over R. In this case now, what we are having is the impedance represented by Z, because we now have not a pure resistance, that is not a pure ohms, but a, um, a, a number that has both the real and imaginary part. So we call that the impedance, and it's represented by letter Z. So in that case, from equation 12, V over I will be what? Equal to the square root of that, R squared plus the reactance squared. So we say from that equation 13, it implies that the resultant reactance will be equal to 2 pi FL minus 1 over 2 pi FC. In other words, means that if you equate it to 0, it means that the 2 pi FL will be equal to 1 over 2 pi FC, all things being equal. So say if a circuit consists of a coil having resistance R ohms and inductance R Henry, then such a circuit is considered to possess resistance and inductance in series. When you have that, the impedance will be square root of R squared plus 2 pi FL squared. If you have three of them in series, like shown in Fig 9, then it will be R squared plus that of reactance, inductive reactance, minus that of capacitive reactance, minus because the voltage produced in them are out of phase. So we say down that based on that equation, it means that 2 pi FL is equal to 1 over 2 pi FC. That is, XL is equal to XC. So when that condition appears, when the inductive reactance is equal to the capacitive reactance, something starts happening in the circuit. And to find that thing that is happening, we isolate the frequency of operation at that point. So if you do that, you see that the frequency of operation at that point will be 1 over 2 pi square root LC. We call that equation 14. So at the frequency given in equation 14, it means that the impedance is equal to the resistance. Remember, in the RLC circuit, we have the R, which is the resistance, and we have the combined action of the inductive and the capacitive reactance, which we call the impedance. So we say at the condition where equation 14 exists, the impedance is equal to the resistance, and I will be equal to V over R. So if the resistance is small compared to the inductive and the capacitive reactances, then the potential difference across them, that is, the potential difference across XL and XC, becomes far greater than the applied voltage. You can see it's possible to multiply the voltage because at this condition, the potential difference across the inductor and the capacitor becomes far greater than what you are applying. So equation 14 is termed the natural frequency of the circuit and represents the frequency with which energy is oscillating backwards and forward between the capacitor and the inductor. This energy is stored as electrostatic energy in the capacitor and a quarter of a second later as magnetic energy in the inductor. So you see, when we talk of self-starting oscillators, you can see that you can use your inductor and your capacitor, apply an energy voltage to it and remove the source. Then the thing will begin to oscillate. If it moves from the capacitive energy straight to inductive energy, back to capacitive energy, back to inductive energy, there you have a circuit called oscillators. So in our future lectures, we also be looking at these oscillators and see how they, come into being. That's, very important because that is what generates your frequency which you use to carry out any operation. So this energy is stored as electrostatic energy in the capacitor and a quarter of cycle later as magnetic energy in the inductor. Now, owing to losses, because when this is oscillating to and fro, there will be losses because it's not operating in a vacuum, so there must be losses. So owing to these losses in the circuit elements, the net amount of energy available in the circuit between the inductor R and the capacitor C continues to decrease as shown in figure 10. If you look at it, you see that the first oscillation, or the amplitude is higher and it continues to thin out with time towards the right. So, and we say this plays a very important role in electric circuits, more especially in communication circuits, and forms the basis for the study of transmission lines and antennas. I will quickly, in the future, talk about transmission lines to see how standing waves are established and how these standing waves and transmission lines give rise to your antennas so that you can transmit with your antenna from one point to take the signal to another point. Now, you will continue to energize, else due to losses, your signal will continue to taper, reduce in strength, in signal amplitude as it moves away in time. So this is a very big concept when you are an electronic communication engineer. So say thank you at this point for listening. Like, share, and subscribe to this channel so that you will get notifications as we treat more interesting topics like this. So also in my next lecture will be really self-test lecture whereby we will ask questions and see how you understand them. It will come in form of multi-choice questions so that you will be able to, answer small questions that may come up as you, try to master the lectures. Thank you for listening.